For things that don't exist, imaginary numbers are remarkable in the power and scope of their application. There is no number that can be multiplied by itself or squared to give -1. Pretending there is, however, gave birth to one of the biggest developments in mathematics. I, the name mathematicians have given to the square root of -1, can be used in arithmetic just like real numbers. Adding multiples of I, or imaginary numbers, to real numbers creates so-called complex numbers. And geometry performed with complex numbers lies at the intersection of many different mathematical fields.
In modern number theory, complex analysis is essential. Without complex numbers, there would be no fundamental theorem of algebra. So you can imagine that algebra would be very much hampered in its development without complex numbers. A lot of modern physics would not be imaginable without the introduction of complex numbers.
In the field of complex differential geometry, Ngaiming Mok, a professor of mathematics at the University of Hong Kong, solved an important problem called the generalized Frankel conjecture. To do so, he developed a powerful new mathematical tool called varieties of minimal rational tangents. Complex differential geometry involves the study of manifolds. Like making flat maps of the surface of the Earth, a manifold is an object that may be curved in any dimension, but can be covered by regions in a flat space, known to geometers as Euclidean space.
The generalized Frankel conjectures concerns the complex structure of a compact algebraic manifold under some assumption on its curvature, which is positive or semi-positive. So in order to solve this problem, I make use of the Ricci flow and algebraic geometry, reconstructing the complex structure of the underlying compact Kähler manifold from its supply of rational curves. From the minimal rational curves, I consider the variety of minimal rational tangents and reconstruct the manifold.
Another major achievement of Professor Mok's work relates to transcendental numbers. These are numbers that cannot be expressed as a solution to a polynomial equation or expression with multiple algebraic terms with integer coefficients. The most important example of a transcendental number is the constant pi.
Most real numbers are transcendental. But if you show me a number in its decimal expansion, it would be very difficult for me to tell whether it's transcendental. As a consequence, showing that pi is a transcendental number is a very difficult problem and makes use of very difficult mathematics, and was a major achievement.
Like pi, the constant e, or base for natural logarithms, is also transcendental. Can one be related algebraically with the other? Mathematicians think the answer is no. This idea can be simply put, but proving it remains an unsolved problem of number theory. Working together with mathematicians Jonathan Peeler and Jacob Zimmerman, Mok has, however, proved a related problem in functional transcendence theory called Ax-Chanuel's conjecture for Shimura varieties.
The Chanuel conjecture is a major conjecture in transcendental number theory. As a corollary of the conjecture, if confirmed, would say that pi and e are algebraically independent. The Ax-Chanuel conjecture for Shimura variety is a function field analog of the Chanuel conjecture. This is a major achievement, and as a matter of applications, major results in number theory concerning rational points have been proven using the theorem on Ax-Chanuel conjecture for Shimura variety that we have obtained.
Since solving the generalized Frankel conjecture, and after returning to Hong Kong, Professor Mok has worked with the Korean mathematician Jun-Muk Wang. Together with their students, the two professors have advanced the varieties of minimal rational tangents, the tool of algebraic geometry that Professor Mok created, and used it to solve a series of long-standing problems in algebraic geometry in an area of the field called uniruled projective manifolds. For developing the theory of varieties of minimal rational tangents in algebraic geometry to solve several long-standing problems and proving Ax-Chanuel's conjecture for Shimura varieties, the 2022 Future Science Prize in Mathematics and Computer Science goes to Professor Ngaiming Mok.